Hey, welcome everybody to part 2 of the Classification of Matter and Properties PowerPoint podcast. Take out your Classification of Matter notes outline and find Roman numeral 4. It should be right after the Law of Conservation of Matter we finished with last time. So first we're going to go through a Classification of Matter scheme to help you decide how to if you look at a substance to decide what kind of material it is. So all of matter we have here can be broken down into either pure substance or a mixture. A pure substance can be one of two things. It can be an element or a compound. You learned about those, I'm sure, in middle school. But let's talk about what those are just a little bit before we move on to mixture. So these will be notes that would go under element and under compound. Okay. Elements consist of 91 pieces of substance that cannot be separated into simpler substances by physical or chemical means. There are 91 naturally occurring ones that include all of these elements except for the ones outlined in white. Promethium, Neptunium, all of these guys are man-made. Technetium in the middle is an odd one. It should be naturally occurring, but it doesn't seem to be, so we can make it if we want it. You might recognize some of these pictures over here, this big chunk of yellow sulfur. This is a emission spectrum for probably neon and from a neon light. This is probably some chromium and maybe some sodium over here. You'll get more familiar with these as we go through the year. Just in terms of what we normally see around us, if you think about just what makes up the earth, we have silicon and oxygen make up most of what we encounter every day. Silicon dioxide is sand, good old sand, and that makes up most of the crust of the earth, with a few of these other things showing up in small amounts. What might be surprising to you is that carbon, which is what makes up most living material, isn't even there. It's not even in the crust, so not at least in these abundant amounts. So just some interesting things. A special kind of element is called an allotrope. I want you to know this term, and I want you to see some examples of it. It's a different molecular form of an element in the same physical state. Probably doesn't mean much, but maybe an example will help. So here are two forms of oxygen and how it exists on planet Earth. One is the oxygen gas that we breathe and we need for life, and the other one is O3, which is present in our ozone layer and also present in smog as actually a pollutant down at ground level. These are both naturally occurring and are called allotropes of each other. One that we're probably even more familiar with is carbon allotropes. Diamond, graphite, and then this last one called carbon-60, which is fondly referred to as the buckyball. It was discovered by, actually not discovered, it was named after Buckminster Fullerene, who is an architect, and he worked with geodesic dome shapes, and so they named the shape after him. All of these materials, the graphite, the diamond, and the buckyball, are made of exclusively carbon atoms. The carbon atoms in graphite lay in sheets that are just electrostatically bonded together, and they work for pencil lead or pencil graphite, also for lubricants for those of you who use it on your bike chains. Diamonds, as you can see here maybe, they've got a similar three-dimensional shape, but then they're bonded tightly to the other layers, which is different than graphite. So that makes carbon in diamond form one of the strongest materials on Earth. Carbon-60 is found often in soot, but studying carbon-60 led people to the beginnings of nanotechnology, and they have used this as a start off for making nanotubes and other kinds of very cool things. All right, moving on to compounds. Compounds are combinations of two or more elements that are chemically combined. That's really important, because if they were just mixed, then they'd still be individual elements. But if they're actually chemically combined and bonded together, then they're called compounds, and they always have that constant ratio. Here are some images of some compounds. And you may have seen things like this. This one up here is water. Then we have carbon dioxide, methane, ammonia, and sodium chloride. I've represented both different kinds of compounds that we'll be talking about mostly this year, which are molecules that are inorganic molecules that are bonded covalently, and then these ions in sodium chloride, which are bonded by their static charge. I have a lot of bonding to learn, but it's really cool stuff, and it gives them very unusual properties. Okay, back to the classification of matter scheme. Opposite pure substances are mixtures. Those are things that are physically combined together. You can have heterogeneous mixtures in which individual substances remain distinct, such as in the salt and sand mixture over here. You can see the sand at the bottom and the murky water above, and so this is what you call heterogeneous. In a homogeneous mixture, the mixture always has a single phase, a single substance that you can't tell the difference between the parts. So mixture means there are parts, but if it has only one phase, you can't tell those parts apart. It's also referred to as a solution. That might be salt water or sugar water or who knows what. You put anything that will dissolve in water. So how can you tell this is a homogeneous mixture? Okay, so what would you have to do to know that there was something in the water? Yep, that's right. If you evaporate the water away, you'll see what's left behind in the water. Kind of like you did on the techniques lab. You would see the solute that was left behind. Sorry about that. Okay, so let's take a little test. I'm going to show you some pictures, and I want you to decide which ones are homogeneous and which ones are heterogeneous. You've got them listed on your outline. A granite, I'm sorry, not a granite rock, a conglomerate rock, a brass candlestick, a hamburger, some Kool-Aid, Pepsi One, whoops. Oh dear. All right, so I want you to write next to each one whether you think it's homogeneous or whether you think it's heterogeneous. Okay, the ones that I would call homogeneous or the same throughout would be the brass candlestick. It's a mixture of metals that look like they're one single metal. And if you're just talking about the Kool-Aid itself, I would call Kool-Aid a homogeneous mixture. It's clear and you can see through it. Everything else I would call heterogeneous, unless, of course, your Pepsi is flat. The bubbles would constitute a different phase, and so I would call that heterogeneous as long as it has bubbles, and homogeneous if it's flat solution. All right. Here's a list of different types of solution systems. So these are homogeneous mixtures made of different combinations of things. So you can have a gas-gas mixture, a liquid-gas mixture, as opposed to a gas-liquid mixture, liquid-liquid, solid-liquid, and solid-solid. So think for a little bit about the different sorts of mixtures that might be examples of all of those. Okay, here's some examples we have listed. Air is a mixture of nitrogen, oxygen, and argon, gas-gas mixture. Gas-liquid is when you've got, say, a carbonated beverage. You've got carbon dioxide in solution with a liquid. So the gas is dissolved in the liquid. Whereas if you have a liquid dissolved in a gas, that would be sort of like moist air. Water droplets in the air, vapor in the air, steam. Liquid-liquid could be vinegar, acetic acid in water. You can have solid in a liquid, which would be like the sugar in your drink, in your tea, and solid-solid like the alloy that we talked about with the brass. Some other examples of those metal-metal mixtures are alloys. Many of our coins are alloys. Most metals that you come across are alloys because it's expensive and not always useful to have a pure metal. They have better properties when you can mix them and get the best properties out of the different metals. All right, so that is our classification scheme. This is similar to what we just put together, only just flipped over. The mixtures and the pure substances are on opposite sides. So one thing that we can think about using this scheme is how we might separate the mixtures that are made, and because that's an important thing in chemistry, is being able to separate something out that you need, and because most things come in mixtures. So if you want to go from a mixture to a pure substance, you can do a physical change, separating them out. The only way to go from a compound to an element or vice versa is with a chemical change, because remember that involves bonds. Okay, we're going to go through a few different ways of separating mixtures. The first way is something you already tried, filtration. It's when you have a porous funnel filter paper that is a barrier to separate the solid out. There's many different kinds of filtrations, but the standard one is what you already did, and we'll be using that method quite a few times this year. Distillation is the way you can get two liquids apart. As long as they have different boiling points, you can separate liquids. Here is a picture of a distillation column. We'll be doing some distillation later on in this unit. So if you, for instance, were making your own grain alcohol, you'd separate the boiling points of the water and the alcohol, and one would boil first, the alcohol would boil off first, and as it comes through this condenser tube, it would cool down with the water that's in the jacket around it, and you can separate that out before the water evaporates away and boils off at a different point. This is done in a very large scale over at Chevron across the bay. They take the crude oil that comes in and they heat it, and as it heats up, different mixtures evaporate and rise. And they rise up, and then as they cool down, they fall onto these plates, and then they can be drawn off at different cooling levels. So the heaviest stuff is the asphalt, and it just stays at the bottom. Then you've got your lubricating oil, like your car oil, heating oil, kerosene, jet fuel, gasoline's way up here, petroleum gas. And as you go up, you would probably even find lighter things like propane and methane. Another way of separating substances is called crystallization. That happens in the earth. You're lucky enough to live in a place where you might actually find crystals mixed in with rocks. And those crystals have been developed through crystallization. So when you have a hot part of the crust of the earth, it will heat up and melt certain substances rather than others. And then as they cool, sometimes they all stay together in a single pocket. Chromatography is a technique that you may be familiar with. It's a technique that separates the components of a mixture on their basis of the tendency of each to travel or be drawn across the surface of another material. This is a cool lab that maybe you did in biology or AP Bio, where you take some plant material, the chlorophyll, and you concentrate it on a piece of paper and you let it rise up, and different chlorophyll compounds will settle out at different times because they're more or less attracted to the paper. All right. In the last topic, we want to get a little quantitative here and tell you how you can tell if something is a compound or a mixture using their masses or their weights of the parts. Okay, one thing that helps us understand if something is a pure compound is the law of definite proportions. It says that regardless of how much compound you have, it's always composed of the elements by the same proportion. So if you have water, a teacup full or an ocean full, you always have the same proportion of H's to O's, 2 H's to 1 O. Doesn't matter how much you have. And you can do that mathematically if you can separate out the compounds, or the elements, sorry. You would do that by finding the ratio of the mass of each element in that compound once they're separated. And that's where we have to do a little percent calculation. Percent is always mass of the part over the mass of the whole. So percent of the mass in a compound is going to be mass of the element over the mass of the compound, and then times 100 to make it a percent. So I want you to try a practice problem. If you've got a 134.50 gram sample of aspirin, it's made up of 6.03 grams of hydrogen and 80.70 grams of carbon and 47.77 grams of oxygen. What's the percent by mass of each element? Okay, I'll walk you through one. So if we want the percent hydrogen, we're going to take 6.03 grams of hydrogen and divide it by the mass of the whole compound. In this case, it was 134.50 grams. So you divide that out, multiply it by 100%, and that would give you the percentage of hydrogen in that sample. So go ahead and calculate that out. Try the percent of carbon, the percent of oxygen, and I'll wait.
Oh,
come on.
What?
That's my son in the background.
No, you're going to edit that.
All right, here's the answers. She had 4.48% hydrogen, 60% carbon, and 35.52% oxygen. If you had trouble with that, make sure you write a note and we'll go over some more practice problems in class. Okay, last part. We're almost done, folks. It's called the law of multiple proportions, and that was important because it turned out that not all elements combined only in one way. So for instance, you can see these compounds down here, nitrogen and oxygen. This compound is NO, 1N to 1O, and this one is NO2. Two gases, two very different sets of properties. And in order to tell one from the other, chemically, you'd have to find their percent compositions. And it turns out when different compounds are formed by the combination of the same elements, different masses of one element combine with the same mass of the other element in a ratio of small whole numbers. That sounds really complicated. Let's look at an actual example. So let's say we have two samples of compounds made only from hydrogen and oxygen. They have the following compositions: 15 grams hydrogen, 120 grams of oxygen, 2 grams of hydrogen, and 32 grams of oxygen. First, let's decide if these are the same compounds. If they're the same, they're going to have the same percent composition, right? So why don't we calculate the percent hydrogen in each compound? So this will be compound A. So for the percent hydrogen in A is 15 grams of H divided by the total compound would weigh 15 plus 120 and then times 100%. So what is that? 15 divided by 135 grams is, okay, 15 divided by 135 gives you 0.11. If you multiply that times 100%, gives you 11% hydrogen. And if you want to find out your percent oxygen for that same compound, you could just easily do 100 minus 11, which is 89% oxygen. All right, so let's try compound B. Percent hydrogen in B would be 2 grams over 34 grams when I combine the 2 and the 32. Times 100% equals, still having a hard time writing on these. I got 5.88 percent hydrogen. I don't want to erase all of it. Anyway, 5.88% hydrogen. So the conclusion is, nope, the ratios are not the same, therefore they are not the same compound. That's the end, folks. Have a good evening. We'll talk more about this in class. Thanks. Bye.
Done.